Okay, hello, welcome to part 3 of the College Algebra Exam 3 review. So we're going to be starting on number 29. So on number 29, there actually is a small error in this problem, and this Fahrenheit needs to be 100 degrees Fahrenheit, because as we see, if we did 50, we'd somehow get t equals 0, which is not exactly what we're getting from the purpose of this. So now that we have that, that's going to be the temperature of the steel. So we're going to sub that in for big T. So 100 equals 50 plus 1550 e to the negative 0.05 t. I'm going to want to solve for t time, the amount of time it will be that it's been removed. So we're going to minus this 50 over. We're going to get 50 equals 1550 e to the negative 0.5 t. Then we're going to divide by this 1550, and 50 divided by 1550 is 0.3225 equal to e to the negative 0.5 t. Then in order to get this e base to go away, we're going to take the natural log of both sides. So the natural log of this, and then we'll have negative 0.5 t, and then we're going to divide by this, and we'll get t, and t will be, so natural log of our answer divided by negative 0.05. You're going to get 68.6797. So in this case, we're not going to look at this. So t is in minutes, and so we're probably going to round up those minutes that we get the full time that we definitely know that it's been out without heat protection. So we're going to round to the nearest minute. So we're going to round this to t equals 69. So it took 69 minutes after the steel was removed. Okay, let's look at 30 part A. So we see that we have the log on both sides of this equation, and it has the same base. So therefore, we can actually set them equal to each other. So it's kind of like if we had something like this equal to that, we'd set 7x equal to 2 because they have the same base. So the same thing we're going to do here. Since they have the same base, we're just going to set them equal to each other. And then we're going to solve for x. So I'm going to move this 4 over, and I'm minus this 2x over. So 7x minus 2x equal to 1 plus 4. So then I'll have 5x equals 5, and I'll get that x equals 1. Okay, so we got for that one, we got x equals 1. And then we're going to move on to the next one. Okay, for part B, we see that we have the natural log of x plus the natural log of x minus 8 equal to the natural log of x minus 20. So we see here that we have a plus symbol, which will now turn into, if we combine them, it multiplies in the inside of the natural log. So then we have this equal to the natural log of x minus 20. So now that we have that, we have something where it has the same base, kind of like the top one. So we can actually just set the inside equivalent to each other. So then we have to where we need to FOIL this out. We get x squared minus 8x, and then equal to x minus 20. And then we'll have 8x squared minus 8x, and we're going to move these over. So minus x and then plus 20. So now we have it to look quadratic. If we simplify this, we have x squared minus 9x plus 20 equal to 0. And then we also have, and we have to FOIL and get this out to where we have 2 x's to find solutions for this. So now that we have that, we know that we have 5 and 4 that can give us 20. By multiplying and adding them, we get 9. But they both need to be negative, so where we get this negative 9 and the positive 20. So x equals 5 and x equals 4. So the thing with these problems is that we also need to plug back in these answers to see if these answers qualify. So we have natural log of 5 plus the natural log of 5 minus 8 equal to the natural log of 5 minus 20. So we see the problem here with this is that if we simplify these two expressions, we'll get the natural log of a negative number, which is not allowed. So we can't actually input these x values. And then if I put in 4, 4 is still not greater than 8 and not greater than 20, so we'll have negatives. So there are no solutions for this part B. Okay, moving on to part C. Okay, so we have the log of 4 of 5x minus 13 equal to 1 plus the log of 4 of x minus 2. So we're going to kind of want to get things that look alike together. So I'm going to move this log here onto the other side. So log of 4 of 5x minus 13 minus the log of 4 of x minus 2 equal to 1. So with this one, I'm going to actually want to do, with them having the same log, I can actually combine them. So since we have a minus sign, in order to combine these inside of the log, we're going to make it 5x minus 13 over x minus 2 so that they're the same. So now I want to get rid of this logarithm. So we're going to actually do this to the power of 4. So then I will have 5x minus 13 over x minus 2. And if that's going to be that, I'll have this is just 4, because this is going to be 4 to the power of 1, which is just 4. Then I'm going to multiply this over. So then I'll have 5x minus 13 equal to 4 times our x minus 2. Distribute this out. 4x minus 8 equal to 5x minus 13 minus the 4x over minus the 4x, and then add the 13 on to the other side. So then I will have x equal to a 13 minus 8, which is just x equals 5. So now we have solutions for all three of these, and we should probably account for the idea if I put in 5 here to make sure the solution works. So putting 5 into here, if I put the 5 in here and then a 5 in here, this will be 25 minus 13. So our log will stay positive, and then 5 minus 2, which will be 3. So our log will stay positive. So 5 is able to be input into a log. So x equals 5 will be our solution.
Okay, number 31. A teaching method to teach vocabulary to 6th graders involves students working in groups on an assignment to learn new words. After the lesson is completed, students are tested for retention at 1-month intervals. It has been found that the average score, S of t, can be modeled by S of t equals 94 minus 18 natural log of t plus 1, where t is the time in months after completing the assignment. If the average score in a monthly test is 65, how many months has it been since the assignment was completed? Round to the nearest month. So t is in months, S of t is our score, so we have that 95 is our score, or sorry, not 95, 65 is our score, which is equal to 94 minus 18 natural log of 1 plus t. So we need to go ahead and solve for t. So first thing that we can do is subtract 94 from 65 and get negative 29 equals negative 18 natural log of 1 plus t. Oops. So then next we can divide it by negative 18 to go ahead and get that 1.611 must equal the natural log of 1 plus t. So now we can take everything to the e power, and if we have e to the 1.611, we get 5. And then this will equal 1 plus t. So now if I subtract 1 from both sides, I get that t is equal to 4. So we found our answer is 4 for t, but what does this mean? It means the assignment was completed 4 months ago, essentially, because t is in units of months. Okay, next one, A, we're going to solve the following literal equations for the indicated variable. So we have this equation, we just need to solve for k. Oops. So the first thing that we can do is go ahead and move that 78 to the other side to help isolate k. So if we have t minus 78 equals 272 e to the negative kt. So next we can divide everything by 272 to get t minus 78 over 272 equals e to the negative kt. Our next step is we take the natural log of everything. So now we have natural log of t minus 78 all over 272 equals negative kt. So we want to solve for k, so let's divide out negative t. So our answer is going to be negative natural log t minus 78 over 272 all divided by k. This is equal to, oops, not k, t. Is equal to k. So we found our answer for k, and that is that k equals negative natural log capital T minus 78 over 272 all divided by t. So then for our next one, we have that s equals 90 minus 20 natural log of t plus 1. And this one we're going to solve for t. So first thing we can do is move that 90 over. Say that s minus 90 equals negative 20 natural log t plus 1. So now let's divide everything by negative 20. And we can also go ahead and multiply everything by negative 1 first, just to make things a little bit nicer looking. Say that 90 minus s is equal to 20 natural log of t plus 1, and then divide everything by 20. So next, we need to take everything to the e power. So e to the 90 minus s over 20 equals t plus 1. So now we just subtract 1, and we get our answer that t equals e to the 90 minus s over 20 and minus 1. And that's going to be our answer. Okay, number 33. The population of Canada in millions was 30.7 in 2000 and 38.2 in 2020. Write a function for p of t equals p naught e to the kt to model the population p of t in millions of Canada t years after 2000. We're going to round k to 4 decimal places. So the best way to start this is to recognize that p naught is like our initial principal, or our initial amount. It's going to be 30.7. We can find this by setting t equal to 0. We just get that p naught equals whatever our amount is at time 0, which is 30.7. So then next, we need to use this piece of information that we were given to go ahead and solve for another part. So we know that p of 20 is equal to 38.2. So 38.2 is equal to our initial amount, 30.7, e to the k times, well, we plugged in 20 for t, so let's write 20 here. So now we need to solve this out for k. So the first thing to do is divide 38.2 by 30.7. And that gets me 1.2443 equals e to the k times 20. So now we can take the natural log of everything. Go ahead and say that 0.2186 equals 20k. We can divide everything by 20. We found that k is equal to 0.0109. That should be rounded out. So we have k now, but the question asks us to write p of t. So p of t is equal to p naught, which is 30.7, e to the k, which is 0.0109, d. That's going to be our answer for part A. Okay, 33, part B. We're going to use the model from part A to estimate the population in 2028. I went ahead and wrote our model right there. So what we need to do is just plug in what year it is. And notice t is years since 2020, or 2000, sorry. So t is going to equal 28. So what we're trying to find is p of 28, which which is going to be equal to 30.7 e to the 0.0109 times 28. So now we just have to type this into our calculator. Say 30.7 e to the 0.0109 times 28, and we get that p of 28 is equal to 41.69. And if we round to the nearest tenth of a million, that is going to be 41.7. So our answer that we can go ahead and say is that our model predicts the population of Canada to be 41.7 million in 2028.
Okay, for this next one, we are going to write a function in the form of q of t is equal to q naught e to the negative kt, where t represents the time since introduction of the bacterial agent. And we're going to use this above information to do that. So it tells us that the population decreases by half every 6 hours. So we can use that to help us make this equation. So we start with 2 million, and we know that. So if we have 1 million is equal to 2 million, because that's our q naught is 2 million, e to the negative k, which is what we don't know, but we know that it takes 6 hours to do that. So solving this equation for k, we're going to divide by 2 million. Divide by 2 million. So we're going to get 1/2 is equal to e to the negative k to the 6. And we're going to take the natural log of both sides so that these cancel. Natural log of 1/2 is equal to negative k times 6. And then we're going to divide this by negative 6. So then we get k is equal to the natural log of 1/2 over negative 6. When we put it into our calculator, we'll get 0.1155. So that's our k, which means our equation is going to be q of t is equal to 2 million e to the negative 0.1155 to the t. So now it says use the model from part A to determine how long it will take for the bacteria to decrease to 100 and round to the nearest hour. So we're going to sub in 100 is equal to 2 million e to the negative 0.1155 times t. Now we're solving for t. So we're going to have 100, divide both sides by 2 million. Then we get 1 over 20,000 is equal to e to the negative 0.1155 to the t. We'll take the natural log of both sides. So natural log. So the natural log of 1 over 20,000 is equal to, these are going to cancel, negative 0.1155 times t. We're going to divide by negative 0.1155. And then that's going to give us our t, which is equal to 85.7 hours. But it says round to the nearest hour, so it's going to take us at least 86 hours. So this next part is going to have us write this equation as an exponential equation. So what we do is we write our exponential form, and we're going to set it equal to this equation. And what we can do is just plug in any t. We can plug in something like 1, and then we're going to solve for k. So we're going to take the natural log of both sides. That's going to cancel. Great. And then we're going to just divide by negative 1. Putting that into our calculator, we get k is equal to 0.000428. And if we plug that into our equation, we get e is to the negative 0.000428 times t, and that will be our new q of t.
The population of California, P of t, in millions can be approximated by the logistics growth function. P of t is equal to that mess, where t is the number of years since the year 2000. Determine the population of California in the year 2000, round to one decimal place. So in function notation, that'll be p of 0, because it's been 0 years since the year 2000, is equal to 95.2 over 1 plus 1.8 e to the negative 0.0180. Plug that into the calculator, you'll get 34. And then this will be 34 million people. B, predict the population of California in 2028. So that means it's been 28 years since the year 2000, so it'll be P of 28. So 952 over 1 plus 1.8 times e to the negative 0.018 28. And that is going to be 45.6, again, million people. C, use the model to determine the year when the population of California would reach 68 million. So we know our answer is 68. 1 plus 1.8 e 0.018 t. So I'm going to multiply across and then divide. So we have 1 plus 1.8 e to the negative 0.018 t is equal to 95.2 over 68. We'll subtract 1 from both sides, so we get 1.8 e, negative 0.018 t over 68 minus 1, and that will simplify to 27.2 over 68. Divide both sides by 1.8. 27.2, 122.4. Take the natural log of both sides. The reason why we take the natural log is because this is e, and that will cancel out with the base. And we'll erase some of the stuff here at the top to make room. Okay, so we'll get negative 0.018, t is equal to the natural log 27.2 over 122.4, and we'll divide both sides by that value. And plug that into the calculator, and we will get once we round 84. So this will be 84 years after 2000 or in 2084. What is the limiting value of the population of California under this model? We can read that directly off the function 95.2. Now if we graph it, we'll see that it's has an asymptote at 95.2.
Okay, number 37, for the given data, use the regression capabilities of a calculator, find an exponential function that models the data around the 2 decimal places. So what you're going to do is press stat on your calculator, then edit, and then you're going to close out of that, and then stat, and then calculate on your calculator, and then you're going to go to, I believe it's called Ex3 reg. So this is just saying an exponential regression. And if you follow these steps, it should pop up with a page that says y equals a times b raised to some power x. We've written a little bit weirdly on your calculator, right? What that's saying is just this. And it will tell you that a is going to equal 2.3818. But if we round the 2 decimal places, we'll just do 2.38. And that b will equal 1.503. But rounding the 2 decimals, we'll just do that there. So we would go ahead and say that our regression is going to be y equals 2.38. Clean that up. 2.38 times 1.50 raised to some power x. So now once we have this here, what we can go ahead and do is, it's going to tell us if x equals 9, estimate y to 1 decimal place. So if we go ahead and do this, if you use your rounded answer, if you just use this with these 2 decimal places, you'll go ahead and get that y equals 91 point, if we round the 1 decimal place, 91.5. But if you were to like use 2.381849, like carry your decimals out a little bit further, you might get a little bit different answer, closer to like 93. But this is just the answer that we have purely using what we see here. Okay, 38. The age of a tree t in years and its corresponding height and feet are given in the table. Use the data in the table in the regression capabilities calculator, write a logarithmic model. So what we're going to go ahead and do is same process as last time. You're going to press stat, and then press edit. Then you're going to go ahead and enter your data, and then you're going to press stat, and then you're going to move the page over to calculate. And then you're going to go ahead and find ln regression. So this is a logarithmic regression. And if you do this, it'll tell you that y is going to equal a plus b to some natural log x. And it should tell you a equals 4.863. And b is going to equal 6.351. So now what this means is that our regression, or our equation that we think matches this data best, is going to be y equals, and if we round the 2 decimal places, 4.86 plus 6.35 natural log of x. And we need to adjust something. Notice that up here, our variable is in terms of t and h of t. So we're going to correct that. All of these x values that we were plugging in were really t values, and all the y values that we were plugging in were really h of t values. So this here is going to be our regression. Next, it's going to say that we're going to use this model from A to predict the age of the tree if it is 25 feet high. So that means that our height is 25, so we're going to say h is 25, and we're going to go ahead and solve for t. So to solve for t, we first need to move this 4.86 to the other side. If we do that, we should get, we're not going to really care too much about carrying out all our decimal places. We're just going to use purely this model here. So that'll be 20.8, or 20.14, sorry, equals 6.35 natural log of t. So now we divide by 6.35 to get that we have 3.17 equals natural log of t. So now to solve for t, the last step that we need to do is take e to this power. So we're going to go e, and then we have that 23.85 is equal to t. So we can go ahead and just round this to the nearest year and say that it's going to be approximately 24 years for the tree to reach its height.